So today we are going to be talking about patterns and of our solar system and exploration of the solar system, different ways that we actually explore the solar system. So, like I said, if you're just dropping in now, we have some great videos, some adorable videos. I don't normally play videos on my stream, mostly because of licensing things, but these are all free, open. But I will I'll ask all of you if it's too quiet or too loud. Let me know, because I'm piping it all the way through. Hey, Joel. And the last week, we basically went through the solar system. We talked about the different kinds of planets that we have, little fun facts about all of them, their approximate distances. Hey, Nova. What they generally look like, what they're made out of, what their gravity looks like, all that fun sort of stuff. Now we're going to start kind of getting more into those. So first thing, we're going to talk about some of the patterns. Now, if you were paying close attention last time, you may have started to pick some of these patterns out, but essentially we want to look at the large bodies, like the planetoids, how they act, how they behave, all of that stuff. So one of the things that we notice is that all planets are nearly circular. And remember, that was really important when it came to sort of Kepler and Galileo and all of that, them realizing that they aren't perfect circles. That screwed up all of their predictions, but that, they're close to being perfect circles. Hey, Grass Vortex. Yeah, learning. All right. And then all planets orbit in the same direction. If you're looking top down on the solar system, it always takes me a second. They orbit counterclockwise. It's the right-hand rule. And, hey, Mappo. So I think that's right. I always want to say it's going this way, but it's actually going this way. But they all go in the same direction. That's really the big takeaway from that. And then most of the planets rotate in the same direction which they orbit. So if they're going around the sun like this, they're also rotating like this. They're going in the same direction, and the sun also rotates in this direction. Now, next week is when we're going to kind of break these details down into why they do that and what the formation and how this, lends itself to clues about how the solar system formed. But right now we're just taking it slowly, and we're talking about these as just generic patterns that we're noticing. We're not inferring anything yet. These are just the patterns that we're starting to pick out. So all the orbits are nearly circular and nearly in the same plane. So they're all kind of in a flat plane here. They all orbit in the same direction, and then most of them rotate in the same direction. We'll talk about those exceptions in a second. And then large moons, these significantly larger moons, also exhibit similar properties in their orbits around the planet. So these ones that, if they were on their own, especially the ones going around gas giants, they also exhibit similar properties. They're in the same plane, they rotate in the same orbital direction, and they all go around the sun in the same direction. So that would be things like, Titan, Triton, Enceladus, Europa, those big moons around the gas giants. That's kind of what we're talking about there. Now, going on from that, we did notice that there are two really major types of planets. Now, this is Astronomy 101. So if you're watching this and you're like, I freaking knew that, that's okay. Some people might not. So stick with me here. We're still going to get into some cool stuff. And I promise we have some videos that are going to make you cry if you're a space nerd. So the two types of planets that we see are terrestrial planets. These are the rocky planets. That's when we talked about Mercury, Venus, Earth, and Mars, that's what we mean by terrestrial planets. And then we have, they're small and dense. They have rocky surfaces, an abundance of metals, and they hardly have any moons and no rings around them. Jovian planets are what we call the gas giants. So these are the ones beyond the asteroid belt. We have Jupiter, Saturn, Uranus, and Neptune. They tend to be much larger in size, but much lower in density. If you remember, kind of that radius to mass ratios were very different. And then they do have rings. All of them have some type of rings. And they have many moons around them. They lack solid surfaces, and they're mostly made up of hydrogen, helium, and then particularly Uranus and Neptune have hydrogen compounds. And by that we mean water, methane, and ammonia are really the biggest ones there. So, and then they are jovial from all their laughing gas. Exactly. All right, so we have our terrestrial planets, we have our Jovian planets. The other objects we have out there are asteroids. So these are rocky bodies that orbit the sun, but they're much smaller. And if you remember, we talked about the dwarf planet thing. We don't have to get into details with that again. If you missed that conversation and you're wanting to, I don't know, express your opinion, that's fine. You can find the link. I have my YouTube channel down below. You can find the video from last week, see how we distinguish asteroid from dwarf planet. All of that stuff. We don't have to rehash the whole thing again here. But essentially, we define asteroids as rocky bodies that orbit the sun, but they're much smaller. So we have that asteroid belt between Mars and Jupiter. Then we also have comets. Comets orbit the sun. They're mostly made of ices that are mixed with rock. So asteroids, comets, that sort of delineation, dwarf planets. The Kuiper Belt has a lot of all of the above. They have a lot of, if you're technically saying a comet is just an icy, rocky body that's mostly ice, then yes, the objects in the Kuiper Belt are technically comets. Now they're not coming in super close. They're not getting these big tails. It's more when you're just looking at the composition of them. That's how we would define it. And there's at least 100,000 icy objects that are out past Neptune in what we call the Kuiper Belt, where Pluto and Eris and some other dwarf planets reside. Just making that clear. And then the Oort Cloud is where you find a lot of comets. Now, we didn't necessarily talk that much about the Oort Cloud last week. The Oort Cloud extends beyond the Kuiper Belt, and it actually goes out to about 1 light year past the sun, which is freaking far, man. And it's mostly spherical. So when we've been talking about, we have the sun, we have the terrestrial planets, we have the asteroid belt, we have the Jovian planets, we have the Kuiper Belt. Those are all in one plane. And then you have this Oort cloud that extends all the way out, exactly, grass vortex, to about 1 light year. Now, the closest star system to us is 4 light years away. So the Oort cloud extends to about a quarter of the distance to the nearest star system. And the important thing is that it's all spherical. And this is where you think of your more traditional comets, where we see the comets come in close, as many of us have seen in the last couple weeks. They come in close, they start to get a tail forming, and then they zip around and they go back. But the important thing when we kind of determine where comets are coming from is that we can trace their orbit and we see that it's closed. So if you trace their orbit, you can kind of go back and say, okay, that's going to stop, turn around, and come back. And of course, the recent comet that we were all watching, we know has an orbit of 6,000 years. So it's got some traveling to do. That's the next time it's going to be back here. But because comets come in outside of this plane and they still have a closed orbit, that's what made us realize that there is this Oort cloud out there that contains these icy objects and that it's a spherical shape. And there's a ton out there. So, and yes, Andrew, when we talk about exoplanets, we'll get into more detail, but you commented, the order of our planets is a bit of an oddity compared to other planets they found. And that has a little bit to do with the selection criteria of how we detect exoplanets, because the only ones that we're able to detect right now are really big. And the way that we're able to declare them as like an actual exoplanet is that we have to see their orbit a couple times. We have to see that it's a repeating thing, a repeating phenomenon as it's orbiting. And so from that, we only have 10, 15 years worth of data that we can go through to actually find exoplanets. So something like, Saturn, which has an orbit of 27 years, we wouldn't be able to actually see. So there's some question about how common is our solar system versus the selection criteria of exoplanets, but we'll get into that when we get into that chapter. But it's a really, really good point. Right now, the exoplanets, the star systems around other stars that we're detecting are not fitting the mold of our star system. So that is an absolute question, but thank you for bringing that up. So I mentioned that there are some exceptions to this rule, to these rules, to these patterns that we're seeing. The first one is that Uranus is tipped on its side. So all these other planets, remember we said most of them rotate in the same direction they're orbiting. Uranus is on its side, so it rotates like this as it goes around. So it's the whole concept of days and years and all of that gets kind of screwed up when you're, when you're talking about Uranus. We see that Venus rotates backward, again, talking about going around the sun. Its rotation, Venus rotates backwards, but really slowly. It's like it takes longer to rotate around than it does to go around the sun. So a day is longer than a year on Venus, and it's in the opposite direction. And Asdelin asked the question, does that mean something hit Uranus? That's what we think. And the same thing with Venus, because their orbits are not in the same direction, or their rotation is not in the same direction as their orbit, that they are these exceptions. We think that there may have been some thing that occurred that would have tipped it on its side or caused it to rotate in the opposite direction. And again, the key is it's not just because it's rotating in the opposite direction. Venus exhibits all the other same properties as these large objects. It's just going in the opposite direction super slowly. So again, the theory is that maybe something hit that to knock it in the opposite direction. Definitely space wizards. I like that. And then these small moons do have unusual orbits. So things that are going around that aren't these, massive bodies that on their own are kind of comparable in size to maybe Mercury or Pluto or some of the dwarf planets. The smaller ones are going all around in different directions. And, technomages, that's definitely it. And planetary kind of succinctly summed up, we don't know how weird our solar system is because there's a lot out there that we're still discovering, which is exciting and very cool. And then our moon is freaking weird. When you think about it, right, we were going through our solar system and we were talking about like terrestrial planets, Jovian planets, very clear patterns, rocky, metal, gas, rings, no moons except for like one massive moon compared to the ratio of its parent planet. And then, Mars has 2 tiny moons, but they're like tiny little potatoes that go around in weird orbits. The moon is like a huge chunk compared to to Earth, to our planet. And so that's actually a huge exception. And we'll go into kind of the thought about where it came from, how it formed and all of that. But that's like one of those puzzle pieces that doesn't quite fit most of the places you're putting it. So you're like, something's got to be up here, something here. Yeah, Andrew, and then the fact it's tidally locked, that all of those details we'll unpack next week and talk about the formation and particularly where the moon came from. I like the class 1 civilizations. Good thoughts. All right. So going on from here, we're now going to take the next sort of, I don't know, maybe 20 minutes, talking about spacecraft exploration of our solar system. This is, Astelin, the moon may have been a buddy that hugged its proto-Earth friend too tight. Aww. So the spacecraft exploration of the solar system, this is a poster that I actually have behind my green screen. That's the cosmic, I could look at it, but I'll tear up the green screen, that shows the patterns that every single spacecraft has taken through our solar system. It, is very, a lot of us own it. It's very, very cool. The amount of detail in here is just bonkers. The fact that you can see, so this is every single spacecraft that we've sent out to explore our solar system and all of the paths that they've taken to get to their destination. So not just where they were going, but all the paths that they have taken on the way. We talked a little bit a few weeks ago, so I'll kind of do a recap, about gravitational slingshots and conservation of momentum. So remember, when we're sending things out into space, one of the things we can do is utilize the gravity of other planets to adjust the speed and the direction that spacecraft are going. For some of these, this can extend almost decades onto their trips, but if they're having to line up very precisely, sometimes those decades worth of going around other planets to adjust your trajectory and not needing all that fuel in order to do so is actually very cost effective, in a kind of a counterintuitive way, but really, really cool, and allows us to visit lots of parts of the solar system as well as get some nice free gravity assists around other planets. There you go, domestic. I like that. Yeah, and the fact that less delta V, you want to get your speed the way that you need it. And it's free fuel, essentially. And remember, if we treat these as collisions effectively, they're not physically colliding, but the entering of the gravity well and then getting slung off in another direction is a transfer of momentum. And so you're able to kind of treat it as a collision. And because the mass differentials between the spacecraft and the planet are so big, the planet is losing some energy in that transfer, but not enough to significantly affect its orbit. And Lake Girl, yes, so using gravity assists helped with Apollo 13, I believe. It's been a while. I was meant to watch that movie a while ago, and I did not, because it left the services I was going to use it on. So, yes, thank you for the confirmation, Andy. So they did use gravitational slingshots. One thing I did watch that is fictional, but I did watch more recently, was The Martian. And they talk about using the gravity assist around the Earth to go back and pick up Mark Watney. And Comedy Forecast asked, the amount of momentum we steal is small, but do you think it will ever become an issue? Not really, because it's hard for us to wrap our brains around how massive these planets are. But if you think about the spacecraft that we, send up, they're super tiny sitting on these launch pads compared to the Earth around it. And so it's fairly negligible. This is like, as the random flybys that you get from asteroids and other objects and comets and everything else in our solar system is going to negate, if not contribute more than a spacecraft would. So I think it's pretty negligible. But I mean, I guess the thing is like, if we consciously send a spacecraft at the same point in our orbit every single time, which would be very hard to do to the same planets in their positions, then you could eventually screw it up. But yeah, that would be, it all really would even out. That would be too specific to feasibly be able to do. But that's a really good question, though. I appreciate that. Yeah, I think you're right, Andy, that there was a society against Venus slingshots. Mappo, that's a really good point. Said, is it a bit like calling solar panels non-renewable because the sun will eventually stop emitting light? I think that's actually a fairly apt comparison. Again, just because of the randomness of the directions and everything that we're going in. Yeah, exactly. Or wind turbines causing climate change. So yeah, the gravitational slingshots are something that we see and use all the time. Now, what I want to go through now is the different types of robotic spacecraft that we send into the solar system. So we looked at all of the stuff we've sent out there. They're all not necessarily the same thing. So we're going to go through a few, and I just realized I forgot to add an example sample return mission because we don't have that many of them, but we have actually done it. Stardust. So I will come back to that. That wasn't a code name for a Star Wars event that's about to happen. It's called Stardust. So yeah. But I will talk about it. I just don't have any cool visuals of it. It is, Becca. So brace yourself. I actually didn't put the saddest one up there because that is guaranteed to make me cry. The other ones that I'm going to play have like an 80% likelihood that I'm going to get overly emotional. So, yes, thank you, Planetary. So there's the link to Stardust if anyone wants to check those out. But let's go into details on what flyby missions are. So first, let me go through these. There's 4 really types of spacecraft that we send into space. We have flybys, we have orbiters, we have landers or probes. We can kind of lump together. Depending on who you're talking to, the way that we talk about them are a little bit different. And we also include rovers in that. And then these sample return missions. So I'm not wild about the way that this organizes it. I would break in the landers to landers, probes, and rovers as 3 different things, but they're all touching the surface, I guess, is the way we can think about those. So flyby missions, these ones go past a world and continue on their merry way. They take pictures as they go and don't stop for gas. Quite literally, actually. So they're cheaper. You don't need as much fuel to be able to enter orbit, to do any of that stuff. That's actually a significant amount of, cost limiters to missions. And with flyby missions, you just fly past, take pictures, and go on your merry way. This also allows you to visit multiple planets. So when we talk about the other ones like orbiters and landers and all of those do have to eventually get to a destination. A flyby mission can just go by. And Andrew, Voyager. I actually found one of the coolest things, and I can't believe I hadn't found this before, but I will pull it up when we get to our examples, and it is awesome. And then orbiter missions, these ones have destinations. They still might use gravitational slingshots. They may still fly by other planets, but they have a destination to go orbit and spend significant amount of time there. They have long-term study. They have sort of similar, equipment that flyby missions have. Cameras, spectrographs, instruments. So spectrographs, remember, because we're taking Astronomy 101, we talked about spectroscopy a couple weeks ago, so that's what a spectrograph is. It's doing the spectroscopy of the atmosphere, of the surface, any of that stuff. And then orbiter missions can also have radar equipped onto them for planetary objects, planetoids, planets or moons that have atmospheres that make it hard to see the surface, particularly Venus and Titan. And I'm going to show the video of the Huygens probe actually landing on Titan, but Cassini had radar systems on it as well to be able to see the surface. And then we have, like I said, these lander probe missions. You can break them into landers, probes, and rovers as 3 distinct sort of different things, but they usually all get packaged together, which is why I think they package it together here. Basically says you're designed to land on the surface or probe the atmosphere, but you're entering the atmosphere at some point. This allows you to have surface views to monitor weather, to perform automated experiments on the surface or in the atmosphere. So it's like you're taking samples and you're performing experiments on them, which you're not able to do in an orbiter or a flyby mission. Some of these include rovers, so particularly with Mars, but let me just kind of break down a little bit of a difference between them. So the way I categorize them with landers, probes, and rovers. So let's talk about probes first. I would say that probes don't necessarily have to land softly. It's probably the way I would categorize it. They can probe the atmosphere, they can probe the surface, but they don't have to do it pretty. Lander is designed to land, so to softly land, and if anyone had a Commodore 64 like I did when I was a kid, you had that Mars landing game that you had to adjust which I know is also has many iterations since then, but that's the first one I remember. Trying to land the thing onto the surface of the planet is really, really hard, but that's a lander. And then a lander gets to its spot and it plants. It's like, I'm here, I'm good. And then rovers, like I said, are sometimes coupled with landers where they land, open up, they go on their merry way like Spirit and Opportunity did. But Curiosity, as we'll see here, actually was just a rover in its own right, which is pretty cool. But still softly had to land on the surface. And we've sent these to the Moon, Venus, Mars, and Titan, as we will see. And then, so they did that with, I have all of my examples, so for these specific questions. And if anyone remembers these, throw them in the chat too. There were a couple. One plowed into a comet and then picked up the information Yeah, deep impact. So, Grass Vortex, the one you're asking about is Deep Impact observed its lander, which was really a probe, impacting Comet Tempel at 10 kilometers a second. That is not a soft landing. That is a... and then we've been observing Mars, too, for so long that when we've accidentally or purposely crash things into it, we can see the results from that too, or go back and see the results. But yeah, that is quite the speed. So 10 kilometers a second. That was Deep Impact, and that was in 2005. This is why I had the Sandy. So thank you. Made it all worth it. Thank you, Mohammed. That is 22,000 miles per hour. It's fast. All right. So I said I was going to bring up this really cool thing that I found. This, and I can make it full screen, is a current status of Voyager 1. Flying through the cosmos, doing its thing, progressing on its mission, and you can look back to see where it is relative to the solar system. I think this is really, really cool. This is just the... Yeah, thank you. I thought this was really cool. It says kind of where it was. It's been interstellar since 2012, that it's a flyby mission. And then we can pull up Voyager 2 and see where it is. And it is slightly further away. Slightly different direction. But looking back at the solar system like that. So, it's so lonely out there. Oh, Andy, that's awesome. Boeing saved Space Camp. Yay. So yeah, mind blown. This stuff is really cool. And you can find, this is just directly off of the NASA Voyager website that you can see all these details here. And Voyager left the solar system in 2018. And you can see this is 1977. It's been around as long as Star Wars has. Flying through space, all on its lonesome self. As Asdeline pointed out. It's so lonely and dark out there. So now that we're all sad, we're going to feel so many feelings. It's quite dangerous, actually. All right, I'm going to talk briefly about Messenger. So now we'll go through a few orbiter missions. Yes, Deep Space Network, you can actually get data back. I think you can also get data. I'll pull up the Juno one as well. But thank you for that link. So people can check out that link. You can actually get data through from Voyager. That's sending data back, which is awesome. All right, so Messenger is studying Mercury, and it's found some really cool things. Last week I talked about how we've discovered in the polar craters that never see sunlight because they're too deep, we found frozen ice, even though Mercury's hot, because it never sees sunlight, and that was information that Messenger found. Oh, yeah, Andrew. Oh, bring in the Star Trek references. The Star Trek movie, don't remember which, but a Klingon ship destroyed an Earth Voyager-like probe. Was that an episode or was that a movie? Do you remember that? Was it Star Trek motion picture? Oh, yeah, and Voyager from motion picture. So many homages. Star Trek 5. Thank you, Comedy Forecast. This is why I have you all here. I appreciate that. Excellent. So Messenger, I've just got some details there. It's no longer operational. I don't think it's no longer operational. It went 29 times around the sun. It flew by 6 inner planets. And then it made 3,308 orbits of Mercury, which is pretty impressive. You guys are the best. That's why I wiped it from my brain. Magellan, I really like. So Magellan is an orbiter mission of Venus, and this is one that had radar on it. So this is radar images of the surface of Venus, which is just, it's just spectacular. It's spectacular. It's why we get excited about space. It's why we love it. And, yeah. All the feelings. The MRO, Mars Reconnaissance Orbiter. This has been at Mars for a while now. This is actually a probe of the depth of water ice on the surface of Mars. So this is the type of thing that the Mars Reconnaissance Orbiter can study even from space. Like I said, things like spectrographs and radar systems will allow you to get this sort of information. One of the main things that the Mars Reconnaissance Orbiter is trying to figure out is what happened to the atmosphere on Mars, which is like one of my favorite things to talk about. We talked about a little bit about it last week as well, but this idea that Mars has had water on the surface, it has water ice on the surface. It had water on the surface for a very long period of time, and we know that because of once again, the layered rocks that I can never remember what it's called. Starts with an S. It's not stratospheric. I always want to say it's stratospheric. Every time I actually talk about these legitimately, I always have to put that word in my side. Sedimentary. Thank you. Muhammad wins the prize. The sedimentary rocks. The fact that Curiosity found sedimentary rocks on the surface of Mars shows that not only was there liquid water, but there was standing liquid water for a period of time. So the Mars Reconnaissance Orbiter, one of its primary missions is to probe the atmosphere to try to figure out what happened. Mainly, was the loss of atmosphere due to a catastrophic instantaneous event that happened, or was it a gradual decay as the planet cooled off? Because it's half the size of Earth, so it had to have a magnetic field at some point, which meant that it had to have a warm core in it, and because it's half the size, one of the theories is that it just cooled off. If you take 2 loaves of bread out of the oven, one's half the size of the other, the smaller one is going to cool off first. And so when it cooled off, the magnetic field disappeared and the atmosphere got blown away. That's one of the theories. And so the Mars Reconnaissance Orbiter is trying to probe the atmosphere to see any sort of residual, like if there was any stuff that could be indicative of maybe an impact that got flung up into the atmosphere and then hung out. There's lots of things it can study. So that's one of the things it's doing, but also probing the depth of water ice on the surface, which is pretty awesome. Dawn Spacecraft, we talked about a little bit last week as well. This is one that was going through the asteroid belt, and it primarily studied Vesta, which is an asteroid, and Ceres, which is a dwarf planet in our asteroid belt. So there is an orbiter around Jupiter, which I'll get to. I don't think it has a probe. I know we're intending on sending something to Europa in the future, and I don't think that hasn't launched yet. And Juno is a current orbiter around Jupiter, but I don't, unless I missed the plan on that one. Did it drop something in the atmosphere? I don't remember. This is the sort of stuff I should look up, but I appreciate it. I will search for that once we're done with this, when we're doing our just chatting session. Okay. Gotcha. So another failed funding situation. So Dawn, a few cool things about the Dawn spacecraft, right? This is, like I said, it's an orbiter. It went to go study the asteroid belt. It's technically not in mission anymore. It ended in, it says on there, November 1st, 2018. If you can see that, it says 51,000-ish hours of ion engine thrusting. It's a TIE fighter. No, it has an ion engine, so it literally just like spits ions out the back to push it one way. Very, very slowly. Very slowly. Not space battle-y that we would want, but still pretty cool. So the Dawn spacecraft, single ion engine fighter. I love that. And then remember when we were talking about Ceres before, the fact that like the imager, the camera, picked up these highly, highly reflective sections of Ceres, but the spectrographs and the instruments that it had on it weren't expecting that, and they weren't necessarily tuned to try to figure out what compound that possibly could be. So they'd have to do like some active spectroscopy, and they weren't able to. They took what data they could, but it's still a little bit of an open-ended question. Right now, I think they were able to figure out that it's some type of salt compound, but they didn't have the detailed instruments enough to get any more information than that. So we'll go study it another time. And the Mothership and the Martian. Thank you. So Juno, as Andrew mentioned, that there is an orbiter. Oh, not that one. There is an orbiter around Jupiter right now. And as our brain was blown last week, this arrived at Jupiter 4 years ago, which actually makes me sick to my stomach because I remember it getting there like it had to have been like, I don't know. Time is no longer a thing. But they don't have a fancy infograph or data thing like Voyager does. but lots of cool information. And the main thing is, now I prefer the term community science, but they have this data up here that you can actually go through and get data yourself and process images from Juno. So Juno is around Jupiter. It's got some really cool, like I said, there's images here, media gallery. They just took images of Ganymede's North Pole. So this is an ongoing mission. It's only been at Jupiter for 4 years. So there's still lots and lots of data that we can get from it and learn about it. Yeah, Becca, astronomy would be pretty hard without that. Concur. All right. So that's Juno. Now I'm going to play this video. So Juno is sort of the successor to Cassini. Kind of similar sort of mission. Orbiter missions, long durations, lots and lots of data that they're getting, and even just a lot of imagery. Cassini taught us so much about Saturn. Rest in peace, baby. We love you. We love Cassini, and it just has taken some spectacular images. But I think it was 2004 when it got to Saturn and dropped the Huygens probe onto the surface of Titan. Because this is what Titan looks like. We can't see under the clouds of it. Yeah, exactly. Jupiter is scary and difficult. And honestly, I think that was one of the main reasons that they chose Saturn first before Jupiter to do a mission like this, is because Jupiter is so massive. There's so much stuff going around it. Cassini could almost be like a mini test version of this. Still lots of information to get, but yeah, there's a lot there. So I'll play this video of going through the surface. Now this is a combination. It's mostly radar. This isn't just taking pictures as you're going the way down. These are processed. This is a processed movie that's coming from the images, that combination of data that they were able to get. But done very well, very cool. Easy to check out. So as it's going through the surface, as it's going through the clouds, you can see these like sort of mountain ranges. Now this is, like I said, it's a composition of different types of data that we've got. And as we've learned, it can be radar, using radio waves, using different types of imagery in different wavelengths. But you can see these kind of mountain ranges as it's getting through the clouds and onto the surface. And there's no sound associated with this, by the way. That there is some height to it. There is some depth to it. There is, we've also discovered that there are lakes down here on the surface that are actually lakes made of methane, which is fascinating. And then we've also found, mostly from Cassini's radar data, that these lakes of methane also contain, I think, nitrogen icebergs, which is also objectively awesome, that we've seen these icebergs like appear and disappear in these lakes of methane, which is just awesome. Also from this, the Huygens probe, now remember, it's not necessarily meant to have a nice landing, but it's taking information of the atmosphere as it's going through as well. And it was actually able to pick up carbon compounds in the atmosphere that we didn't necessarily think occurred in nature. We thought that like we could make them artificially in a lab, but they were able to find some carbon compounds in the atmosphere, which was pretty interesting. Yeah, Asdalin Titan is very literally very cool. Oh, you were thinking of the Galileo Probe. Gotcha. Okay, Andrew, thank you. I appreciate that. So you can see this image coming in again. Like I said, these are composite images. And then as it lands, it's one of my favorite things to see. You'll see it land briefly. And then it's still taking pictures, and it wasn't meant to last very long on the surface. So it's taking pictures. It looks like there's an alien shadow monster that's crossed in front. You'll see once it lands. That's actually the cloud of the parachute. And then you'll see some sort of residual heat that's just coming from the lamp from the camera. It's dark here. So this is a camera, and then there's our alien sticking its head in. No, it's the parachute. And then the hot air above the lamp spot, you can see, is the thing that's making it ripple there. So really, really cool. That was sort of the imagery of landing on the surface of Titan. All right. Are we ready for this? I don't think we're ready for this. So Rosetta got to this comet, 67P Churyumov-Gerasimenko, in 2014. And ESA, this was a European Space Agency mission. And what they did is they put together a storybook as it was going through its mission. This is sort of the highlight, and we'll just play it. Just enjoy. Tell me in the chat if it's too loud or too quiet. I can turn it up.
After a 10-year journey, Rosetta and Philae had finally reached their destination, Comet 67P, Churyumov-Gerasimenko. Rosetta's exciting mission was to follow the comet as it traveled around the sun. She would learn all about the comet and how it changes as it gets warmer and warmer, while Philae would visit the surface. But as she got closer, Rosetta realized that the comet was much more complex than people had thought, using telescopes from far away. It almost looked like two comets stuck together, and from some angles its shape was really rather strange. Rosetta had to steer several times to get closer and closer to the comet. The closer Rosetta and Philae got to this strange world, the more wonders they discovered on its surface. There were craters, cliffs, and boulders the size of houses. Rosetta spent many weeks studying the surface of the comet, sending lots of information back to Earth. She also started to analyze the dust and gas around the comet, but there was always one question in the back of her mind. Where was Philae going to land? No spacecraft had ever attempted to make a soft touchdown on a comet. Philae started to pick some of his favorite spots on the comet, but Rosetta had to check with the experts back home. They thought long and hard and eventually found the best spot for Philae to land. Then Rosetta had to plan the exact route around the comet to make sure that Philae would land in the right place. Soon it was time for Philae to make the final preparations for his great adventure. He checked that he had everything he needed to land on the comet. Both spacecraft couldn't wait any longer. The whole world would be watching as Rosetta and Philae got ready for their biggest challenge yet.
Okay. We're ending it there. Because I cannot bear the next video. These are all really good. I thought that was like the best way of describing the mission from a orbiter / lander standpoint, taking up all the data and everything. And the next video is so sad. So if you don't remember what happened to Rosetta and Philae, so Rosetta's the orbiter, Philae is the lander. Basically what happened is because this comet has hardly any gravity on it, you saw the spikes as Philae was putting the shoes on. The shoes were meant to hit the surface and basically latch in there. And it landed slightly on its side. So when the spikes went in to land, it actually pushed it up and over, and it landed kind of on its side, kind of under a cliff. And it just didn't, it was still able to do what it needed to do, but it didn't have, it, because of its angle, it didn't get enough solar power for it to actually, like, go through the whole mission the way it was intended. And just to lay it home, this is literally the image that they left it with. Which is just so cruel. So don't watch the last video if you're prone to this sort of thing, because it's like literally the worst thing ever. Like, and we left it there in the dark by itself, and it's so proud. It's got all of its little medals. It's just the worst. So I'm glad you all enjoyed that one. That is one of my favorite, but I love just the visualizations for all the different sensors that it had and the way that it was getting all this information. So with that, as I've broken everyone's hearts in chat, I also want to show this is one of those more empowering, like, space is brilliant thing. I will say the demographics of this video are not great. We're glad the demographics of the space industry are starting to change. So if you notice that, you're not alone. But this video still is fantastic. And I mentioned earlier that Curiosity was a little bit of a unique experiment when it came to rover landings. Because in the past, when we've sent physical rovers out, particularly with Spirit and Opportunity, they landed, they were deployed. They rolled off of their lander and went to go explore Mars. Curiosity did not. They actually used a sky crane. So this is a great video of Curiosity's landing on the surface of Mars. I get emotional watching it. But I'll just play it. It's this, as you'll see, it's artificial simulation of what it would look like, mixed with the people who are actually getting it in there, because we didn't actually have a television crew on Mars watching it land, obviously. I just feel the need to say that. Anyway, here's the video.
Things are looking good. Coming up on entry. Vehicle reports entry interface. We are beginning to feel the atmosphere as we go in here. It is reporting that we are seeing G's on the order of 11 to 12 Earth G's. Bank reversal 2 is starting. We are now getting telemetry from Odyssey. We should have parachute deploy around Mach 1.7. Parachute is deployed. We are decelerating. Heat chill has separated. We're on the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers descending. Standing by for backshell separation. We are in powered flight. We're at an altitude of 1 kilometer descending. Standing by for sky crane. Sky crane is started.
Signal to us, you remain strong.
Touchdown confirmed. We're safe on Mars.
You got thumbnails.
We made it! Oops, I played it again. That was bonkers. That is just, it's bonkers. That whole sky crane thing, it was phenomenal. And, like, Curiosity is just, it's Wall-E. We've sent Wall-E to Mars. It's doing its thing. It has its own personality, and we love it. It's amazing. Yeah. I mean, Andrew, you're not wrong. We're basically just populating another planet and just throwing junk everywhere. To learn. So, yeah, it's always good to be conscious of things we're sending into space, what we're doing to other planets, but I would say, like, that balance we've not been terrible at. We're erring in a direction that isn't great. Oh, thank you, Book Addict. Yay! Yeah, exactly. Mappo, that's a really good question. If anyone knows in the chat why they chose a sky crane over a lander, it could have been just to try a new method of landing, partly as an experiment as well. The other thing I could think of is possibly just the weight ratio, that if you were to have the whole thing land and then deploy it out, that's much heavier. And so just landing it without would be less heavy. And then good question about how Perseverance is landing. And yeah, Curiosity is weirdly huge. And yeah, Becca, for sure. Thinking about garbage in space. It's the size of a small car. It's pretty cool. All right, well, a question about Perseverance. So let's watch a similar video that was released yesterday.
The Perseverance rover headed to Mars, ready to ride a column of fire and smoke on its way to the Red Planet.
And liftoff. As the countdown to Mars continues, the perseverance of humanity launching the next generation of robotic explorers to the Red Planet.
And Atlas TU has gone to closed loop control, standing by for SRB burnout shortly. And we have successful separation of Mars 2020 with the Perseverance rover.
Flight nav.
We now have an acquisition of signals, and the years of blood, sweat, and tears from every person who worked on this mission is now realized as Perseverance makes its way to Mars.
We made it. We made it. Well, we haven't made it yet, but we launched it successfully, so that's been great. And of course, always follow Perseverance rover and all that other fun stuff there. So, a couple of things in here. Active landing, not sure. I was trying to look it up now how it's going to land on the surface because I haven't been able. Oh, I found it. Hang on. All right. And thank you for sharing that. Todd made a really good point about the difference with Curiosity and the other rovers. So Curiosity has a nuclear power system. It doesn't fully rely on solar panels, whereas those other rovers, that's a good point, had to be contained when it landed so then the solar panels didn't get covered in dust. Because the dust on Mars is like the consistency of baby powder. Okay, so it's going to use the sky crane maneuver too. So Perseverance is, going to basically do the exact same thing. And it says it provides the ability to land a large, heavy rover on the surface of Mars. And now our technology is such that it can be a slightly more precise landing. So super, super cool stuff. History is just continually being made. And if you were able to watch that stuff, it's pretty phenomenal. I slept through it. I slept through the launch. Sleep is important too. You can watch it later, but we all have our priorities. This week I've needed sleep. Oh, thank you. Just another guy named Harry. Thanks for the follow. I know. I agree, Andrew. The media people always make them sound like action movies. You should see the trailer for Juno. I didn't put it in here because it's actually pretty long, but they basically turned Juno's mission into an action film trailer. It's really, really funny. It's fabulous. So let me see. I can do it not on my phone. So with that, those were the last videos I had. We can get into questions now. Next week, so we talked a little bit about the patterns of the solar system. Next week, we're going to start unpacking those, what they mean and how we puzzle piece together how our solar system formed based on the patterns that we've seen and what we've been able to deduce from the motion in our solar system. So things like the flattening, the rotation, the orbits, all of that stuff. So it should be really fun. With that, I will end the lecture. We went almost the full hour this time. So if you're watching this recording, if you're watching this after the fact on YouTube, thanks for watching. Like and subscribe, all that fun stuff. Links are down below. You can catch us live Fridays at 1 p.m. Pacific time. Oh, thanks, Book Addict. Yay! You can catch us at 1 p.m. Pacific on Fridays for the live class, and normally we would end with about 20 minutes of questions, but not today. All right, so thanks for that, and we'll catch you next time.